So this is Fibonacci. This is the implementation of Fibonacci that doesn't use recursion, but it uses efficiency. And if you look at the structure is a base case, same thing. This is your base case. If n is less than or equal to 1, return n, right? So this is what? This is your base case. And then what is this? You remember I showed you that table on the side? This is essentially storing those values in a table. Because what I'm saying is, listen, if I'm calculating fib of 0 and fib of 1 or fib of 2, for example, fib of 2 is what? Fib of 2 is, if the table is the value where I'm storing the results of my calculation, then this table here is actually a Fibonacci number. So Fibonacci 2 is basically Fibonacci 1 plus 0, right? And then from 3, for counter is equal to 3 to n, all the way from 3 to n. Each value, every time I calculate a value, I simply calculate it from the bottom up. So if you remember that table that went from here to here, went from 0 to 1 to 2 to 3 to 4 to 5. What I'm doing is I say, I've got my base case, this is my base case 0 and 1. And then when I calculate 2, I store it. So I calculate 2 and put it here. And what is the value of 2? Fibonacci 2 is 1. What is Fibonacci 3? Is Fibonacci 1 is also 1. And then this is what? This is 2. And then this is what? This is 3. And then this is what? This is 5. And so on and so forth. But what I'm doing is, unlike the recursive definition, in the recursive definition, I keep on calling myself. In this definition, as I calculate a value, I store it in the table. And when I store it in the table, so this is an illustration, doesn't have to be here. It can very easily be here. All I have to do is change this. But I've done this so you can clearly see this as an example. And then what I do is I just run through the table and I build it up step by step, piece by piece. And then when I'm done with the loop, I return the entire table, so you have the full series. If I need to return just the nth value, then I'll just return the nth value. What I've done is I've broken this down. I've broken the code down into 3 pieces. The first piece is, if there's a base case, return the base case. So this is your first piece. My second piece is I've created a table. Think of it as an array. Think of it as a list. Think of it as, an Excel spreadsheet. And in that Excel spreadsheet, what I'm doing is that as I calculate my values, I start storing those values so that I can, if I ever need to use those values, I can just reuse them again. So my base case is what? My base case is table 0 and table 1. Fibonacci of 0 and Fibonacci of 1. And then what I do is, okay, now what is my second value? My second value is going to be n minus 1 plus n minus 2. So for 2, n minus 1 is this, and n minus 2 is this. So this would be 1 plus 0. And then for 3, what's going to happen? For 3, this is 3. So this is table 3. Think of this as a Fibonacci number. And what would this be? This would be 2 and this would be 1. Now we've already calculated table of 2 and table of 1. Where have we calculated table of 2? We've calculated here. And where have we calculated table of 1? We've calculated here. We've assigned these values. So we already have these values. We don't have to calculate them. And what will happen with 3? With 3, it's going to be table of 4. And what's this number going to be? 3 and 2. Now have we calculated table of 3? Yes, we have. Where did we do that? We just did that here in the previous iteration. So we have this available. And we also have this available. Where is this available? This is available here. Does that make sense? So you go on through the sequence, and what the sequence would essentially do is allow you to essentially build up your table from the bottom up. The inefficiency that we saw of us calling the same function multiple times for solving items or elements that we already solved for, that inefficiency goes away. The last week and this week, we spoke about patterns and code in data. And what we want you to do is think about is what are some common patterns in code and data. So the common pattern that we looked at with respect to factorial, with respect to Fibonacci, was base case, else return the recursive definition. Sum it all, base case, else return the definition. Fibonacci, base case, else return the same, right? And if we use the same process, the same model for the factorial implementation, then it should be possible to use the similar function, a similar model, a similar approach to build an iterative exercise for factorial. So we've done this for Fibonacci. Let's take a look at for factorial. So now for factorial, if n is less than or equal to 1, return n, and that's your base case. So you do that right up front. So you don't have to do this right towards, you don't have to get into anything else. If you have the answer already, just return the answer. You don't have to move forward with additional lines of code. And then your table base case is 0 for 0 and 1, and then 2 is what? 2 is going to be 2 into 1 factorial. What about 3? 3 is going to be 3 into 2 factorial. What about 4? 4 is going to be 4 into 3 factorial, and so on and so forth. So again, if you see the logic, this is the stored value concept once again, but rather than using that stored value concept to calculate Fibonacci numbers, we're using that stored value concept to calculate factorial. And then same design, same structure, same approach, same method applied to sum it all. If base case, return the base case, otherwise store the base case results and then work up from base case results. 3 different problems, 2 different approaches. The first approach is a recursive approach, which is exactly similar. There's only one line which is different in that recursive approach. The second approach is an iterative approach. The iterative approach is exactly similar. This part of the iterative approach is the same in almost all 3. The only thing that's different is how we store, is the implementation of the equation. And then here is the function that calculates it. So these 2 things are different, but the structure, the design of all 3 approaches is very, very similar. Make sense? Do you see it? Practice quiz question, right? So this is think of this as a midterm question. What you're really tracking is the growth of work required to solve for input n. So as you increase n, right, like when n goes from 1 to 10, from 10 to 100, 100 to 1000, 1000 to 10,000, 10,000 to 100,000, 100,000 to a million, as you increase n. For Fibonacci, your recursive approach, makes you make calls that are 2 raised to power n. But your iterative approach is linear, right? You'll just run, if you think in terms of the number of times a loop would run. So for example, if you go back here, for sum it all, right? How many times do you think this loop will run? So if you think of this as a basic operation, right? If n is less than or equal to 1, what is this? This is a quick comparison. Let's call this as a single operation. This is 1. And then this is a simple assignment. Table 0 assign 0. This is an assignment. These are an assignment. So this is, let's say, 1, 1, 1. So that's 4. And then you've got this counter that runs from 3 to n, right? How many times would this run? This would run how many times? N times. Correct? Make sense? So what is the total number of times this code, this function, when you calculate it, would run for, let's say, a value of n? Sum it all. It'll run n times. So if I give you a value of n, it doesn't matter how big n is, this code will run for n times. There are other variations of this. I've just simplified it. I've just done a very crude approximation. If I look at the crude approximation, you can clearly see that the way the code is structured, there is one big loop in it, and that one big loop will run from 3 to n or from 2 to n. But it'll run for a maximum number of times of how many times? N times. But I think the bigger question now is, which is a question to you, if you go back to the Fibonacci sequence, right? In the Fibonacci recursive implementation, it's not n, it's 2 raised to the power n. Because each call, every time you call, leads to 2 additional calls. So if you go to the higher levels, your tree will keep on rising. So now the question is, For Fibonacci, it's recursive, and for the recursive Fibonacci, it's 2 raised to the power n. For iterative, it's linear. But what about factorial, and what about sum at all? There are no right or wrong answers now, because we haven't done the work that's required to answer this question. But I want to see how many of you go in what direction. For n, you would call it for n minus 1 to 1 call. For n minus 1, you'd call it for n minus 2, 1 call. For n minus 2, you'd call it for n minus 3, 1 call. For n minus 3, you'd call it for n minus 4, 1 call, right? So each function, as you break it down, will lead to an additional call. And what is that? For sum at all is the recursive. So the iterative is clearly linear, because we just did that. But what about the recursive one? The recursive is also linear. What about factorial? N factorial is n into n minus 1 factorial. Same structure. N is to n minus 1, n minus 2, n minus 3, n minus 4, and so on and so forth. So this is also linear. And this is also linear. So it's n, right? So now n is linear, right? Because, so if it was, let's say if it was quadratic, if it was cubic, if it was exponential, it'll be 2 raised to the power n, or n squared, or n cubed, or could even be n factorial. But in this specific case, the 3 examples that we looked at, both recursive and iterative, only one is 2 raised to the power n, which is the recursive implementation of Fibonacci, but our iterative implementation is linear. And our recursive and iterative implementation for both factorial and sum at all 3 of them are linear in nature. And this is a key point. We'll come back to it a little later, but I just want you to remember this. I want you to remember this specific aspect of the conversation, because we'll refer to it just a little further down in our lecture.